controversy for that, and I won't even get into that issue, because the cutoff for 0 point may be much further for many reasons. But the fascinating part is we can now look at Josephson junctions or diodes as being a source of 0 point energy. And he's, of course, saying dark energy equals 0 point energy. So what do you do with the number of different fluctuating systems if you know that the thermal energy really is no use, or the non-thermal energy is really no use if it goes in both directions? Well, electrical engineers like us basically want to use a diode and force it to go in one direction only. And so a thermoelectric noise, it's called, you find quantum noise, non-thermal noise, but basically in any circuit, when you get to the lowest level possible, you get a mixture of both, especially if you're at any temperature above absolute zero. And these three patents I would recommend is perhaps the most significant discoveries that have been patented in this field. For example, metal-to-metal diodes, if you study this Brown patent, 3890161, that'll give you a really good estimation of the engineering approach to applying sheets of metal-to-metal diodes, which basically have very low forward drop and the potential for the application. The Yater patent I'm not that excited about because he has to use a battery to get the thing working. So even though I analyze it in my feasibility study, I'm not recommending it. However, the Capasso patent, which is an AT&T patent, 4704622, is a very solid 0 point energy tunneling diode patent. And what's fascinating about Capasso is he actually acknowledges 0 point tunneling is the only source of activity for that diode. This, to me, was the best patent you could ask for to verify the fact that ZPE is real. Here's a physical device that doesn't work if 0 point energy doesn't exist. And so even though Yater's, as you can see here, this is a Yater diagram with the voltages being applied, there's the best example is perhaps a diode sitting by itself, unenergized except by the 0 point field. And so just recently now, in 2004, Yasutomi in Science Magazine has pointed out there's a number of molecular diodes that are also available. Now these particular ones that we see here are peptide molecular photodiodes, about 1 nanometer. And of course, this would be the ideal to work with a single molecule. But in this particular instance, they also require organic end pieces that are receptors for photo input. So these would not be recommended, but it does give you the appreciation for the fact that molecular diodes are now becoming available. And I feel very excited about that. Let me go a few more minutes beyond this, just so I can then get into the Q&A if I could.
How much you need to wrap it?
About 10, yeah.
Go for it.
Oops. Oh, here we go again. I'm trying to back up. Yeah. Hey. Okay, so to conclude here, we basically are looking at...
Push that button again. So
yeah, thank you.
now it goes back to up and down.
We basically are looking at a number of... Whoops, I'm at... We'll get it straight here. Okay. To summarize the findings and the technologies that are reviewed, at the top, we are looking at, from the Mead patent, for example, I examined microspheres, nanospheres, picospheres, and femtos. And it's fascinating to find physical representations of each of those in nature. For example, on the, I believe it was the nanosphere range, you basically find there's a leukocyte that, or I think it's a micro, yeah, it's on a micron scale. A leukocyte that basically is fighting Casimir forces to maintain its spherical size. And we find many examples of that now that biophysics and quantum physics are being really related. And you can use the E equals mc squared to get an appreciation of the energy that's available in a mass that size. And when you do the calculations, I just had a discussion about this earlier today, that the energy density tends to increase as the size gets smaller. This is a very controversial statement, and we can only state that the physics and the equations predict that, but I can't really defend it because it's counterintuitive. It doesn't make sense. You know, why would we have milli EVs in this realm, and then we got mega EVs in the femto region? But that's what Mead points out, that as his collectors got smaller, he basically had a more powerful system, and zero-point energy constantly predicts that. So we'll leave that, as many parts of zero-point theory has been done. We leave it on the shelf until somebody proves it to us. So after you look at the technologies, what I did is put them in table form and apply the feasibility to each one. The feasibility of the electromagnetic spheres, where you focus, I didn't even tell you about focusing. You can actually focus zero-point energy to a particular area, just like a parabolic dish does. You can do the same with ZPE, which is also gets you thinking, a lot of ideas of increasing effects. These are moderately feasible. I would even see poor. I apply a poor feasibility to these, just because of a number of extenuating circumstances that are involved. The mechanical approaches, which we talked about a few of them, for example, Pinto's approach and several others that involve mechanical systems that move and try to use the Casimir force. There are several, in fact, more than a half a dozen mechanisms where you can get Casimir forces to repel or Casimir forces to attract by changing the magnetic field, the temperature, the permeability, and the impedance, as we pointed out, and the dielectric constant by illumination. So all of those try to apply it, including spatial squeezing and so forth. But together, all of those are moderate feasibility. The highest rating, or I would say high rating, would be applied to the fluid dynamic approach for many reasons, but there are 3 different ones that apply fluid dynamics. And this to me is very exciting because all of a sudden we see an approach of motion. And receiving motion from the zero-point field is certainly everyone's dream, to get to the stars, of course. However, if we want to start today and get engineering nanotech nanobots to really run around like the sci-fi movies show us, the highest feasibility are basically for the thermodynamic approaches, including Goychuk. Goychuk I didn't give you the reference for, but it's in my study. It's Physical Review Letters, Volume 81, 1998. And he essentially describes quantum Brownian rectifiers. And he does so in such precise terms, in terms of the predicted curves and demonstrations, that whereas before we talked about having a voltage necessary, you don't even need that. He proves that all you need is the quantum stochastic dissipation. And so that's the summary. And the recommendations are that we should be pursuing metal-to-metal nanodiodes, and they probably hold the key to using simple transducers that can achieve watts per square meter for delivery. Many technologies, a couple I pointed to, show you how to apply these in 2-dimensional sheets. And of course, then you can stack the sheets. And they're temperature independent, which is a fascinating part. And they work 24 hours a day as well. That's another very important part of all of this. Ratchet-like asymmetries, as we saw, were more related to the thermodynamic approach. But as Goychuk points out, if you get the tight binding crystal lattices, that is perhaps the secret to applying stochastic resonance and achieving rectification. In other words, you get current flow just by applying the correct quantum mechanics on a randomized approach. And the other word for applying it to the Photo-Carnot engine is quantum coherence, where you just look for a phase difference. And that certainly is interesting as well. And the last one is the electromagnetic field effects, which are encouraging for propulsion and transport. So, thank you very much. And if you have any questions, feel free.